NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, everyone, and a very pleasant good evening to you wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the Von Karman series. Tonight, a discussion 45 years in the making. In 1977, the twin Voyager spacecraft left planet Earth to meet a solar system alignment that only occurs every 176 years, and in doing so, taught us more about our universe than we could have ever imagined. Over these generations, an incredible team of engineers and scientists have guided and cared for these spacecraft, keeping them operational through planetary encounters, the heliopause, and interstellar space. Voyager has captured our imagination, it's expanded our understanding of the universe, and inspired us to push beyond the limits of what was once thought possible. I'd like to introduce our questions co-host tonight, media relations specialist here at JPL. Please welcome Calla Cofield.
Thanks, Brian. And everyone watching, remember that this is your space program. We want you to be involved in the conversation tonight. So if you're watching on YouTube, Facebook Live, or LinkedIn, ask questions in the chat box, and our social media team will bring in as many as we can during our talk tonight. If you do not see the chat box, just refresh the page and it should be right there.
Thank you very much, Calla. We're looking forward to that Q&A tonight. Tonight, we're joined by JPL's Director for the Interplanetary Network Directorate, the home organization of NASA's Deep Space Network and multi-mission ground system and services programs. She has over 35 years of experience in spacecraft operations, serving in project manager roles. She has worked in the mission planning and uplink operations on the Cassini mission to Saturn, the Mars Observer Project, and Voyager 2's flyby of Uranus and Neptune. She is the recipient of a NASA Exceptional Service Medal, NASA Public Service Medal, NASA Silver Achievement Medal, and NASA Outstanding Leadership Medal. She is the project manager for the Voyager Interstellar mission, a role she has had since 2010. Please welcome Suzanne Dodd. Hiya, Suzanne.
Hi, Brian. How are you tonight?
I'm fantastic. I love this spacecraft. Let's get started with let's get started with how you got here. How'd you get involved with Voyager?
Wow. Well, Voyager was the beginning of my career. It's really fun to look back on it. Fun and a little bit scary to know how long I've been working, but no, I started working on Voyager right out of college in 1984. I actually started working a month ahead of my graduation, and I joined the project before the Uranus encounter, and I stayed on through the Neptune encounter. I was not on at launch, and I was not involved with the Jupiter or Saturn flybys, but I came in. There was a 5-year gap between Saturn and Uranus, and so the staffing went down, but then it came back up, and I was on that wave of people that came in to catch the last 2 planets of the flyby.
We've talked about this in our kind of planning preparation for this talk about that time in between, but also by the time we visited Jupiter and Saturn, there was an aspirational nature about this mission. There is kind of a long-term joyful goal about this.
I think, Voyager is really 1970s, mid-70s technology. The heritage is based on Viking heritage and design, and the one you mentioned in your intro, that Voyager was launched at this very unique opportunity to be able to get to all the outer planets of our solar system, all Jupiter, Saturn, Uranus, and Neptune. So, and then it would continue on out. As we know now today, not certainly when we launched it, but as we know now today, it actually would cross into interstellar space. So the aspiration is how can we build this spacecraft to make that decades-long journey, and what can we put on it to represent us, to represent the Earth? And if you go to image 21, one of the key things is, and this was done very late in the development of the mission, but the gold record got put onto the spacecraft. It represents a time capsule of us here on Earth, what we were feeling, the different cultures, the different music, the different sounds of the planet Earth. And it was stuck on Voyager, both Voyager spacecraft, and it was put on as a time capsule to be found sometime in the future by whatever beings might be out there. And that part of doing that was an aspiration. Let's take a piece of us here on Earth and send it out into interstellar space, which we've been very successful at doing.
We talk about that aspirational nature, and we talk about 45 years later, and we're still talking about it. We're still communicating with it. But if we could jump back in time, what really was Voyager's original mission? You kind of hinted at it, but how did it start off?
The original mission was only for 4 years. It was just to fly by. It was just to fly by Jupiter and Saturn, and that was its level 1 requirement that NASA had for it. But they knew if they were successful, they had a key target of one of the moons at Saturn, and if they knew they were successful with Voyager 1 flying by it, then they could send Voyager 2 on a slightly different trajectory, which would get out to Uranus and also out to Neptune. And that's exactly what happened. We were successful with Voyager 1 in getting all the science back that we wanted from Saturn. And so Voyager 2 was sent on a different path that was able to acquire data from Uranus and Neptune. And think about it today, Uranus and Neptune were in flybys in 86 and 89. We have not sent a spacecraft back to those planets since then. There's hopes that we can do that in the next 10 to 15 years, but it's really amazing that Voyager was able to accomplish a flyby of 4 planets, but also that no one has sent a planet back there. We didn't know anything about Uranus or Neptune, what we would see, what we would experience, and everything that we know about that from a close flyby of the planet is Voyager data for those 2 planets in particular.
Well, let's kind of keep talking about that a little bit, because the mission has changed, kind of even with those original things. It seemed like it was in the back of everybody's mind to keep going, but how has it kept changing over if you say 4 years and now 45, that's continuous change.
Yeah, certainly. You can see it early on. I came on for the Uranus encounter, and since the mission was designed for Jupiter and Saturn, we had to make adjustments to account for both the longer distances between the planet and the Earth, the communication distances. We had to make adjustments for the light levels. Certainly, Neptune is the sun is much darker at Neptune than it is at Jupiter or Saturn. So we did some engineering changes to the software in order to adjust for the different light levels at those planets. And as you can continue out, certainly the biggest challenge that Voyager has, I should say one of the biggest challenges Voyager has. We have a lot of challenges. We're getting up there in years, so we have a lot of challenges. But one of them is our distance. Where Voyager 1 is 15 billion miles from us. The one-way light time there is 21 hours. So we can't communicate very quickly with it, and the data rates are very, very low. 160 bits per second is the data that we get back, and we have to use nearly every antenna at a DSN complex. So a 70 meter and 3 34 meter antennas all arrayed together to get get 160 bits back because of our distance. So those challenges, the distance challenge really requires the spacecraft to be very autonomous and to have fault protection where it can put itself in a safe state and not expect to be commanded right away. We have to have processes and procedures on the ground where we can get enough information from this sort of trickle of data that we know how to fix anything that might go wrong. One of the things we did after the Neptune flyby is we repurposed the memory that was being used by all the imaging instruments. So the instruments that would take pictures of the planets. There's nothing to take pictures of where Voyager is once it left Neptune. So we basically turned off all those instruments. One, that saves us power, but two, that saves us memory. And we repurposed that memory to be able to put a standard routine of activities on the spacecraft so that the spacecraft just is in essentially a loop of executing all those activities over and over and over again. Where we are now is we're getting very limited on our power. So we've been turning off backup systems and doing some power management that involves only having certain systems, alternating systems on and off with each other. So they're not both on at the same time, taking too much power. And so it's a key, one of the key resources we manage now is the power, because the power margin levels are very low. And the other one is actually the temperature, because it's very cold where Voyager is. And we need the propellant that the thrusters use in order to keep the antenna pointed at the Earth. We need that propellant not to freeze, because if it did, our antenna would drift off the Earth, and then we wouldn't have any more communications. So that kind of gives you an example, Brian, of some of the things we work with and are challenged with today.
I want to take a step back to some of you talked about the imaging and the Neptune encounter. I want to talk about that Neptune encounter and kind of the vibe and the feel. I don't know if there are too many things that kind of mimic that today with science and pop culture.
Yeah, it was just such an electric atmosphere here at JPL, and I think a lot of it had to do with the sense that one, these were flybys, right? So we never seen these planets, and in particular, Neptune is really one of my favorites. I got to be involved with the closest approach sequence for that. And it's really something I look back on as a highlight of my professional career. But the way they did the press conferences during the Voyager days is the press actually came to JPL. They don't do that anymore, right? Everybody's kind of like we are right now. Everybody's Zooming or, talking through computers, but they were there and they were in person. And
we actually have an example of that. If we bring up image 11, we can kind of take a good look at that.
Yeah, so this image shows Ed Stone being interviewed by several press members, and it was about a 2-week period where they would have a 10 a.m. press conference every morning, and the scientists would come and talk about what they were learning and show the latest images. And Von Karman, they did it in Von Karman, and the auditorium was full. Every day it was full. And before that, they had to bring in they brought trailers in for the press to stay in, and you could see some of the really I would say Walter Cronkite, but some of the more famous reporters come and be interviewed, and interviewing people on the mall or interviewing people out in front of the JPL sign, and as you drive in, and there are a lot of reporters around. There was a lot of scientists. There was a lot of activities, and it went on for about 2 weeks. So it was really exciting day. It was great to come to work. I think everybody felt like it was fabulous to come to JPL and see all this and have all this excitement and activity going on. And once you're involved with that, you're hooked. I mean, you don't get that feeling in very many professions, I would say. And I think if you're at all inclined to liking space, just being able to see the work you've done, having it execute, and you have to cross your fingers when you send commands to a spacecraft. It doesn't always work, but in this case, it was basically flawless for essentially for the Neptune encounter, and just really rewarding to have your work shown and people being excited about it. And it's really the whole world. I mean, Voyager has touched the whole world, and it's just led to so much more science discoveries.
I want to stay with Neptune for a moment, because I know you've got a little memorabilia from that encounter, and it made me very happy when you showed me. I just want to show the world.
Okay, you want to see so if you go to picture 13, right? So one of the other really fun parts about the Neptune encounter was, and this is a good image of it, we had a party after the Neptune encounter. It was sponsored by the Planetary Society, and that is actually Chuck Berry, the real Chuck Berry, on the steps of the in front of the mall, in front of our 180, which is the building that the lab director lives in, playing Johnny Be Good, because Johnny Be Good is the hit song on the, well, I should say the hit song, one of the songs on the Golden Record. So one of the things they handed out at that event is a little gold coin, and it's signed. It should say it's a limited edition, so the back of it has a number on it. You probably can't see that, but I've kept this, all along, and it really reminds me a lot about how much Voyager and how much the Neptune encounter means to me, and means to me professionally, but also just as a human being, and feeling like you're able to contribute to society. I think, yeah, I had kids around right after that, and their science books have pictures that Voyager took in them. They still do today, because Neptune is probably there's no other good images of Neptune taken by a spacecraft. Voyager is it. So anyway, it's just it's very humbling and really fun to be part of the excitement of a planetary mission, and I think Voyager has a lot of people's hearts.
It does. I want to come back to that societal impact, but I want to stay with Neptune for just a half second, because that encounter happened, and then how long until we got to interstellar space?
Yeah. So the Voyager encounter was in August of 1980. I'm sorry. The Voyager encounter with Neptune was in August of 1989. I actually left the project after that, and worked on Mars Observer. I worked on Cassini. I worked on Spitzer, and I didn't come back till 20 years later. And the project was still traveling through the heliosphere. So when they sold the interstellar mission in 1990, they basically said, oh, it's about 50 AU. That's where we think you'll cross the heliopause into interstellar space, and that's another. I try to do the calculation. That's another 5 to 7, 8 years or something like that. Well, we crossed at 121 AU. It took us 22 years to cross from 1990 to 2012 before we crossed interstellar space. And I think Voyager was kind of forgotten for probably all of those 20 years. A lot of the same people worked on it. Obviously, the staff was very downsized from the multiple hundreds of people that worked it during the Neptune encounter. I know it got skinny down to maybe 50 or 60 for the next 10 years, and then it got skinny down to like about 15. And really, where we are is in the 12 to 15 range of engineers who support Voyager. And Voyager is 2 spacecraft. It's not just 1 spacecraft. It's 2 spacecraft that are still operating. So that's a very small group of very, very dedicated engineers with really now a very unique knowledge set. So it's incredible that it's lasted as long as it has, but it's in part because of the hard work of the current engineers who have been on the project for decades.
So let's talk about what that is today. How do you, with that decades of knowledge, what is a general day in the life of the Voyager team right now?
Well, we have a daily status meeting, which I think the project has done from day one. Most of the time, it can run anywhere from 5 minutes. It's like a morning meeting, a morning tag up meeting. It runs anywhere from 5 minutes if everything looks good to an hour if we have longer discussions. And actually, in the last couple of years, we've made one of the meetings be more of an engineering focused meeting where there are longer discussions about trade studies and things we're working on, presentations on the different engineering changes we could potentially do. But there's still these sort of 5-minute stand-up status meetings that go on just to check in. What's the next set of commands we're doing? How did the DSN perform during this last pass? Yeah, that's the, and beyond that, then I think the engineers spend their time doing sequencing, building the next sequence, and then also a lot of now it's a lot of analysis about how we can make this spacecraft last as long as possible and go as far as we can into the interstellar medium.
Well, and as you've talked about with me before, that it's also sending back still great science information. It's still very much an alive mission in that sense too.
Right. I mean, we don't fly spacecraft just to fly spacecraft.
Yeah.
Some people probably wish we did, but that's not why NASA does that. We fly spacecraft to get science data back. So as Voyager traveled away from Neptune, it got further and further away from the sun, and eventually in 2012 it crossed the heliopause. Now the heliopause is where the effects of the charged particles from our sun stop and we start sensing charged particles from interstellar space. And interstellar space is really the gas and dust that's left over from exploded stars and all the creation that's going on out there beyond our little cocoon of the sun. So Voyager has taken data really since the Earth, but all the way out to where it is now, 15 billion miles away. It's taken data on how these charged particles change, first within our heliosphere, and now as we go further and further away from our heliosphere, how does the magnetic field of the sun interact with interstellar space? What's the difference in the energy levels of these charged particles? How many are there? And all of those questions that Voyager's answering impact sort of the shape of our heliosphere. Traditionally, the heliosphere has been viewed as basically like an ellipse or a comet shape, where the sun is at one end and the interstellar wind is blowing out the other direction. But with Voyager's information, we can take that data and make a model where it's much rounder. And there's also a model where it's more like a croissant. It kind of has 2 tails instead of 1. So all of those things are possible. It's the importance of the data now is that it's continuing to get that record of change over time. And just like no spacecraft has gone back to Uranus and Neptune, it's going to take 50 years for any spacecraft to get back to where Voyager is now and to get that in situ data.
Okay. That it's So
this is kind of this image right here sort of shows you as we're leaving what the color schemes represent sort of the different aspects of the charged particles and the density of the charged particles that we've seen.
Excellent. I'm just so amazed by the science that's still coming through. I'm amazed by the team, and as you mentioned before about their science books that have these images in it, the societal impact of this, you get some pretty fun fan mail with
Yeah,
Voyager.
I do. It is fun. I have a few of my favorites that I've saved. I got a note from a young girl, like a 4-year-old girl in Germany. Her mother actually wrote the note, but it came with a picture. It came with a picture of Voyager 3, and this girl was describing all the instruments on what that should be on Voyager 3, and one of them was a vacuum cleaner, because we need to sweep up the dust and understand what's in the dust. And literally, she's exactly right. If you dumb down, a fancy instrument, it's a vacuum cleaner. We want to see what the dust particles are made of. We want to capture some and see what they're made of. That's not what Voyager 1 or 2 are doing, but it would be a great thing for Voyager 3 to do. So I have a 4-year-old in Germany, which again shows the wide range of people in the world that look to Voyager for their inspiration. But I also got a fan mail from a gentleman in Texas, who is probably, he didn't really give his age, but I had to guess he's probably 80 to 90. He sent me a $5 bill. He said, "I really, really love the work that you're doing with Voyager, and I want to buy you a cup of coffee and a donut." And he sent me a $5 bill. I returned it with some nice swag, and I said, "Thank you so much. I mean, your letter is enough to make me feel good about what I do, and thank you for your interest in Voyager." But it's great. It's great. I've had people send me pictures of their Voyager tattoos. I won't go into too much detail here, Brian, but there are people with Voyager tattoos that are very proud of them. So,
well, I want to get to that public. I want to get to the folks that are tuning in right now, and I want to see how the Q&A is going. So, Calla, how's the conversation going out there?
We have so many wonderful questions coming in. People just want to know about every aspect of this mission. There's a whole bunch of questions just about communicating with the spacecraft and, how that's changing. So Lorraine on Twitter just asks, what's the length of time to send and receive a message to the Voyagers?
Yeah, I sort of alluded to that earlier, but it's for Voyager 1 is traveling faster, and it's further out. Voyager 2 is never going to catch Voyager 1. So if we just talk about the furthest out mission, it's one-way light time. So the time it takes a signal to go from the Earth to the spacecraft is over 21 hours. What that means is that the round trip right time is 42 hours. So it's nearly 2 days from the time you send a command to the time you receive an answer from the spacecraft that it got the command. And if you think about it, talking to the moon is maybe 3 seconds. Talking to Mars is 20 minutes. So, we're measured in multiple days now at very low data rates. So we can't really say much either. But that's a challenge, and again, it means that the spacecraft has to be very autonomous and do a lot on its own, and that's how we've restructured the mission and for the spacecraft to be able to be autonomous.
And on a similar note, Rob on Facebook asks, because you mentioned earlier that the signal is getting fainter the further these things go from us, and you mentioned that you have to configure all of the antennas at these DSN sites. So is there a limit? How long do you think you'll be able to get a signal from Voyager?
There is a limit, but there's also the ability to add antennas in on the ground to array more antennas. The Deep Space Network is actually expanding. They're putting in a fourth 34-meter antenna at each of their sites, and we'll be able to array 4 34 meters with a 70 meter, and that gives us 3 or 4 or 5 more years. But there is a limit. There is a limit, but we're probably not going to hit that. Or if we get close to that, let me just say it this way: if we get close to that limit, we'll just keep adding more assets on the ground. We'll find a way to array other antennas. We can array maybe something like the Very Large Array with the DSN. We've done some of that in the past. The Neptune encounter, actually, they did some arraying of antennas that don't belong to the DSN with the DSN antennas, just to get that very faint signal of data out. So I don't think that the ground is going to be a limiting factor to the life of the mission.
Well, on that note, Abigail on Facebook asked a question that I'm sure a lot of people want to know. How far do you think the Voyagers will go?
Well, again, there's 2 spacecraft, so that in itself is amazing that we have both spacecraft operating for 45 years. I certainly think we can get to 50 years with probably with both spacecraft, and we're really pushing. I would call it a stretch goal. That's management speak, right? A stretch goal is to get Voyager 1 to 200 astronomical units, and that would be 2035. And that's going to take a lot of luck and good fortune and good engineering, but it's possible. Nobody would have thought that Voyager would last for 45 years. So what's another 15 years, right? So it certainly is possible, but we'll definitely make it to the 50th anniversary and come back and do another show. So.
All right. I have an interesting question here from Daniel on Twitter who says, why can't Detroit get this kind of mileage? So I guess I would maybe translate that as like, how do you build a vehicle that lasts 45 years and 14 billion miles?
Okay, so I think if you bring up image 3, it's probably the best picture of the spacecraft, maybe. But there's a book called Voyager Tales, and it was written after the Neptune flyby, where it did firsthand accounts of the people that worked on the project and people who worked at JPL, just kind of in their own words what they thought of the project. And when you read that, you read multiple times where people would they knew the mission was supposed to be 4 years, but if they had the opportunity to do anything that would make it last longer, to get it to Uranus, to get it to Neptune, they would do that in the process of building the spacecraft. So they would put in higher rated parts. They would, put extra shielding or do extra testing just to make the spacecraft as robust as possible. And I think that points to the whole development team and engineering team at the time wanting to make this project a success and wanting to get it at least get it out past Neptune. I'm not sure that anybody thought it would get into interstellar space, and certainly not 45 years worth of lasting. But I think there was a real sense that we want to make this spacecraft as robust as possible, and we're going to do everything we can to do it. And that was from the lowest level engineer up to the project manager.
All right.
And I can't speak to cars, so
I won't make you. A question that multiple people have, including Randy on Facebook, is what's the most surprising thing that Voyager has seen or done?
So that's a popular question, but I also think it's in the eye of the beholder. If you ask the different scientists who have worked on Voyager, everyone would give you a different answer. And I think You know, if I've listened to many talks by Ed Stone, who is a project scientist here for the last 50 years. Voyager, every time Voyager, they had a question, and Voyager, I'm trying to say this correctly, Voyager provided more questions than answers, right? Every time they flew by a planet, they saw something new, whether it was volcanoes at Io, the first body outside of our Earth that we saw active volcanoes on, you know, rings around Uranus and Neptune that we had never seen before. I think if you bring up image 15, you can see, I personally like this image because it was one that I was involved with taking. But you can see this giant blue spot. Everybody knew that Jupiter had a great red spot. Well, so Neptune has a giant blue spot. Nobody knew that, and so just the interactions of the atmosphere and the ring systems. Certainly, every planet and every flyby had a discovery that was new and got us asking more questions about what we knew about our solar system. And the same is true for interstellar space. You know, there were models. I mentioned that, you know, the differences in the models of the shape of the heliosphere, but there were also models about the density of the plasma and how that changes as you go out from our heliosphere. So that doesn't match what we thought before Voyager got into interstellar space. So we're rewriting, you know, scientific history or scientific discoveries. And I think Voyager is a voyage of discovery, and I think that's its real legacy.
That's great. Thanks, Susie. Another question that a couple of people have asked, including one intuition on YouTube, has the rate of travel decreased, or have the speed of the Voyagers decreased over time?
No, the Voyagers have the same speed that they have from their last planetary flyby. So for Voyager 1, it was the Saturn flyby that has it left Saturn, and if as it left the gravitational pull of the planet, that's the speed that Voyager 1 has, and the speed that Voyager 2 has is from its flyby of Neptune. They don't speed up or they don't speed down. It's a constant velocity.
Okay, Susie, a couple of people asked a question like this, including Mai on Facebook. Because I know you've said that, you know, the Voyagers are 45 years old and there have been challenges with keeping them going this long. So what was the most exhausting day on the Voyager mission for you, or the most challenging?
That's an interesting question too. You know, we have some long days when we get some data back that doesn't look like what we expect. Then we have to spend some long days talking about what's the next set of commands we want to send to help diagnose what we might be seeing. And I think the Voyager project is a constant balance now between the power margin and the thermal. And so we're always discussing that, because you can imagine you could save power by turning something off. We have a digital tape recorder on Voyager 1. It still works. We still use it. But we could turn it off to save power, but we wouldn't want to do that because it's also a heater. It's like a light bulb a little bit. You know, if you turn your lights off, your house gets cold. You can use your light bulbs as heaters. So we use certain parts of the spacecraft to keep those propellant lines warm. So we don't turn that off all the way, because we want the warmth that's coming from the electronics to keep the propellant lines going. So there's a balance, and I think that's been an ongoing engineering task that we've been working on to balance for 6 or 7 years now.
Thank you, Susie. All right, we had one more question. and I have lost who asked it. Crystal on Facebook asks, what will happen when the power runs out? So what will actually happen, when the spacecraft have done as much as they can do?
Yeah, the transmitter on Voyager is a 20-watt transmitter. Basically, it's about the power level of your refrigerator light bulb. But it takes about the transmitter takes 20 watts of power to operate. I'm sorry, I said that wrong. It takes 200 watts of power to operate. And once we get down to that level, we won't be able to get signals from the spacecraft anymore. So we talked about, we've been turning off instrument heaters now for the last 3 years to save power, and the instruments are still operating, which is remarkable because they've dropped in temperature by about 60 degrees Celsius. So they're very, very much colder than what they were tested at, and colder than what they were designed to operate at. But they're still operating, which is another remarkable thing about this spacecraft. But we will eventually be turning off instruments as well to save power. And the last instrument will leave on, and we just will eventually not get a signal from the spacecraft. And that's how the mission's going to end. We could probably predict, maybe within a year when that happens, but and that's assuming that we don't have some other anomaly or something else doesn't break. But if the spacecraft's operating fine, what's going to happen is it just eventually will go silent. And that will be a very sad day.
That is going to be a very sad day. It's actually a very sad moment because this is all the time that we have for our talk tonight. Susie, and all of our meetings up until this point, I could have talked to you for hours and hours and hours, but I want to
have a lot of stuff I could keep going, but you'll have to have me back, Brian.
We'll always, anytime. So folks, that is all the time we have for tonight. If you join us next month, we're going to be talking about the OWLS Ocean Worlds Life Surveyor. I'd like to thank Calla and everyone behind the scenes who make these talks possible. But most importantly tonight, I would like to thank the tremendous Suzanne Dodd for sharing her passion, her intellect, and her care for this transcendent mission. Thank you to all of you for joining us each and every month. Stay safe, stay kind, stay curious, and we'll see you in September.